All right, let's get started. Welcome to the first colloquium of the spring semester. It's my great pleasure to be introducing Nicole Halpern. Nicole is a theoretical physicist at the National Institute of Standards and Technology. She's also a fellow of the Joint Center for Quantum Information and Computer Science and an adjunct assistant professor at the University of Maryland. Nicole completed her PhD at Caltech, winning the International Ilya Prize for a thermodynamics thesis. And after Caltech, she moved on to ITAMP, Institute for Theoretical Atomic and Molecular Physics, as a postdoctoral fellow at Harvard University. During her work there, she won the International Quantum Technology Emerging Researcher Award. She's got several awards already at this early career stage, including the US Aspire Prize, Mary Somerville Medal, and inclusion in the Science News 10 to Watch list for early and mid-career scientists. Today, I think you'll hear about Nicole's re-envisioning of 19th century thermodynamics for the 21st century using quantum information theory. She has dubbed this research quantum steampunk, after the steampunk genre of art and literature that juxtaposes Victorian settings with futuristic technologies. She's described this vision, this field, in a book for the general public called Quantum Steampunk, The Physics of Yesterday's Tomorrow. And this book won the Prose Award for Popular Science and Mathematics. Nicole's popular science communication is not just limited to her book. Actually, the way I got to know Nicole was via her contributions at the Institute for Quantum Information and Matter at Caltech, where they run a website. And Nicole has been a frequent contributor since 2013. I believe she left Caltech in 2018, but she's still the most frequent contributor to this popular science blog out of IQAM at Caltech, and I really enjoy reading her contributions there. Okay, without further delay, I'll leave the stage to Nicole. Very excited to see your talk. Thank you.
Thanks very much for the warm introduction, and thanks for the invitation to be here. I've had a lot of fun over the past few weeks interacting with a number of you here. So you might be wondering about this image on this slide. It's here because I think of this talk as really being, if not your stereotypical great-great-grandmother's thermodynamics. So in the first place, what is our stereotypical great-great-grandmother's thermodynamics? It was captured, I think, evocatively by this writer, Sam Kean, who wrote that when he was a college student taking a thermodynamics class, his class began with a quote from Einstein. It said, "Thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown." So this student thought, wow, that's what Einstein says about thermodynamics. It must be really exciting. However, even Einstein's imprimatur couldn't glamorize the grubby details of heat and work exchanges. So according to this writer, thermodynamics is arguably the most successful scientific theory in history, and virtually no one cares because they're all so bored by it. So am I doomed to bore you for the next 45 minutes? Well, let's take a step back and ask what thermodynamics actually is. I find that a lot of physicists don't know the definition. I had to look it up a few years ago. Interestingly, especially when I've stood in front of a room full of people who say they do non-equilibrium quantum thermodynamics, they don't want to volunteer a definition. So in case you haven't seen it in a while, the definition of thermodynamics is basically the study of energy, the forms that energy can be in, and the transformations amongst those forms. And those forms include heat and work, and associated concepts like temperature. Another complaint by this writer is the name thermodynamics evokes images of Victorians in stuffy suits tinkering with steam engines. So I agree with the Victorians and the suits and the steam engines, but I don't think that necessarily all of them were stuffy. Now, relatedly, thermodynamics was inspired by the Industrial Revolution. Engines were powering factories for the first time. They were transforming the face of civilization. Naturally, people wanted to understand how efficiently they could operate. So the theory of thermodynamics was developed. But even though it started out with practical questions, it ended up shedding light on fundamental questions like, why does time appear to flow in only one direction outside of science fiction. Yet another complaint by this writer is that thermodynamics is a far cry from the enigmatic koans of quantum mechanics, which we can all agree are fascinating and absorbing. Over the past few decades, the enigmatic koans of quantum mechanics have been codified in quantum information science. By that, I mean the study of how we can use quantum phenomena to process information in ways that are impossible if we have only classical systems. By quantum physics, I mean a number of things: the entanglement, the very strong correlations between quantum particles, how operators can fail to commute with each other, the discreteness of spectra, how measurements disturb quantum systems, and even more. By process information, I mean solve computational problems, communicate information, secure information cryptographically, and store information in memories. Just as there are information processing tasks, there are thermodynamic tasks, such as powering factories and cooling systems and charging batteries. We know from quantum information science that we can use quantum phenomena like entanglement to enhance information processing tasks, so we can ask how we can use quantum phenomena to enhance thermodynamic tasks. For example, we can design and build quantum engines, batteries, and refrigerators. And we can ask, how can quantum resources help us in thermodynamics? Also, the laws of thermodynamics were developed by people who had in mind large classical systems like steam engines, so we can see how the laws extend and maybe become more precise to quantum systems. For instance, we can use tools from quantum information theory to derive more refined, more precise variations on the second law, which again helps us understand why time flows in one direction. We can also look at a system that's processing energy and other thermodynamic quantities and ask, what behaviors does this system exhibit just if it's quantum? So we can use thermodynamics to understand better the division between the quantum world and the classical world. These I think of as the guiding questions of quantum thermodynamics, which is a field that's a home base of mine. Quantum thermodynamics has exploded over the past 15 years. The field has grown enormously in theory and in experiments. If you're interested in an introduction to a field as a whole, then I can recommend this textbook and these two review papers. And there's also this book that Alt mentioned, which is for the general public, but scientists belong to the general public. And I should spend maybe a minute on the steampunk aspect. So steampunk is a genre of literature, art, and film that has Victorian settings like Sherlock Holmesian London and the American Wild Wild West and Meiji Japan, together with futuristic technologies like time machines and automata. So it has the old and the new. And I think that quantum thermodynamics is the real-world version of steampunk, because we have thermodynamics from the 1800s and quantum information science, which is partially cutting edge and partially futuristic. We don't have a large-scale quantum computer. So basically, to entertain myself, I peppered this talk with a bunch of steampunk artwork. If steampunk isn't your favorite aesthetic, I'm sorry, but it can be entertained, so hopefully it'll at least keep you awake. All right, most of this talk is about a problem inspired by basic undergraduate statistical mechanics. In undergraduate statistical mechanics, and in a lot of physics, we think about a small system interacting with a big environment. The two exchange things. If they exchange just heat, then the small system will probably thermalize to a canonical state. And when I say state here, I mean a quantum state, so a density operator, which we can think of as a matrix relative to our favorite basis. Technically, a trace one positive semi-definite linear operator. The trace one means if you measure the state, you'll get some outcome. The positive semi-definite means if we take this matrix and we calculate its eigenvalues, we'll find that they're all real and at least zero. And the linear just means this is a particularly simple operator. And suppose that the small system and big environment exchange heat and particles, then the small system will probably thermalize to a grand canonical state. For instance, if you got tea before the colloquium and you set the tea down, a cup of tea down on the table, then the tea would exchange heat and H2O molecules with the surrounding air until coming to be at the same temperature and chemical potential. And we can play this game for many different exchanged quantities and many thermal states. These exchanged quantities are conserved globally across the system and environment composites, so I'll call them charges. I'll label them as Q and index them with A. Now, this exchange leads to thermalization, which is ubiquitous. It happens very commonly to many, many systems. I mean, we currently are far from equilibrium because we do things like eat cookies and then radiate heat to our environments. But eventually, everyone in the room will die, and so thermalize. And so thermalization is a very important universal phenomenon. And thermalization goes hand in hand with the experience of the arrow of time, a very fundamental concept. And it turns out that in some thermodynamic arguments, we are representing these exchanged quantities by Hermitian operators assumed implicitly to commute with each other. This assumption is implicit. It turns out to be in derivations of the form of the thermal states and in the Onsager relations, which tell us what happens if you poke a thermodynamic system not very hard. But one of the really interesting things about quantum theory is that it has operators that don't commute with each other. This non-commutation leads to measurement disturbance and uncertainty relations. So we're kind of obliged to ask, what happens to thermodynamics if the dynamics conserve charges that don't commute? This question came up at the intersection of quantum information theory and quantum thermodynamics about a decade ago, when we realized it seemed not to be asked. And the question has led to a small growing subfield that my group wrote a forward-looking perspective about last year, 2 years ago now. Here's where I'd like to go in the rest of this talk. First, I'll give a concrete example of a system and an environment exchanging non-commuting charges. Then I'll give a brief historical overview of the little subfields. I'll talk about what changes in thermodynamics when charges don't commute, and then talk about opportunities for future work. I think there are a lot of very rich opportunities. What time am I supposed to stop with the slides? $50-minute mark. Okay, then I will probably cut out the historical overview. So here's a concrete example to put a picture in our minds. It was proposed in this theory paper. The theory was realized experimentally in the lab of Christian Roos and Rainer Blatt in Innsbruck, Austria, with trapped ions. And this other theory paper has an extension. So consider a chain of qubits, quantum two-level systems. They might be formed by two energy levels of an ion. We can designate as our small system as some subset of those ions, maybe two of them. The whole thing consists of n copies of the small system of interest, so the other copies form an effective environment. The whole thing forms a closed quantum many-body system whose internal thermalization we can study. To introduce some natural charges, I'll denote by sigma aj, the eighth component of the spin of qubit j. We can form global charges by taking each spin component and summing it across the lattice. Now we need a Hamiltonian that has three properties. It should conserve all of these global non-commuting charges. It should take charges that are local and hop them between subsystems. And the Hamiltonian should be non-integrable, so it should allow the whole state to explore the available Hilbert space if we want to draw any conclusions that we would want to call thermodynamic. We can build such a Hamiltonian. We know the forms of the raising and lowering operators for the z component of the spin. And we know how to build an operator that takes a quantum of the z component of the spin from site j plus 1 and hops it onto site j and does the reverse in superposition. We can form analogous operators for the x-type charges and the y-type charges. We can form our Hamiltonian by taking our hopping operators, summing them over the charges, summing over the lattice, and introducing a hopping frequency. You might recognize this factor as the Heisenberg interaction. The Heisenberg interaction has been well known for a long time. As shown here, it can be experimentally simulated. Although I was just talking with Joel Moore this morning about how even over the past few years, it has turned out to hold mysteries. So maybe it has more mysteries in store for us. But if you still find, well, okay, so I haven't seen the Heisenberg interaction written in this way to show explicitly that it locally transports non-commuting charges and conserves them globally. But if you're still bored by the Heisenberg interaction, then you can go to this paper and find a way to generalize this Hamiltonian construction process for many different classes of charges that don't commute. And if we want to make this Hamiltonian non-integrable, then we can either give the lattice more than one dimension or extend the interaction beyond nearest neighbors. Does anyone have questions at this point? Okay. Then I think I'll skip the historical overview. Maybe just mentioning two parts of it, I think. So the first mention I know of in the literature of anything like non-commuting charges is in this paper by E.T. Jaynes. He wrote two papers in 1957 about information theory and statistical mechanics. The second one is the quantum one. In these papers, he codified the principle of maximum entropy, which leads to the form of the thermal states. That state is the state that achieves the greatest entropy of all the states that satisfy some constraints we know about the system. One constraint on every state is normalization, but also we might know, say, a state's average energy and average particle number. This von Neumann entropy represents our average uncertainty about the outcome of a certain measurement of the state. If we maximize it, subject to these constraints, we find the state that achieves the maximum is the grand canonical state, so the relevant thermal state. Now, Jaynes noted that this principle of maximum entropy works even if the observables don't commute with each other, and that was most of what he said. He had one paragraph about this topic, and when I read that paragraph, I thought, why did you stop here? This is the most interesting part. Nobody ever talks in thermodynamics about the situation where we would have these types of quantities that don't commute with each other. So there was work to be done. He didn't talk a lot about the process of thermalization or what sorts of systems might realize this state. He had some acolytes who tried to follow up but ran into a mathematical problem. And then I found it really interesting that I didn't find any other literature about this problem for decades. Quantum information theory motivated us to think about this non-commuting problem. It's not clear that the system should it's not clear that it makes sense to write down a thermal state in this context, because Jaynes, strictly speaking, wasn't talking a whole lot about thermalization. He was just talking about a situation in which we know certain pieces of information. So eventually, we concluded it makes sense to write down a thermal state. We call it the non-abelian thermal state. The non-abelian is here because these charges that don't commute with each other generate a non-abelian algebra. This state is an instance of the generalized Gibbs ensemble. Probably some of you know that term. If you don't know it, don't worry about it. But the state looks as you might expect. It has an inverse temperature, a Hamiltonian. This is a sum over the charges. Mu alpha is an effective chemical potential. QA is a charge, and the partition function ensures normalization. And since then, this notion of non-commuting thermodynamic charges has been extending into other subfields. So what have we learned? What happens to thermodynamics when charges don't commute? I'll provide a small glimpse of what's been discovered. And the main takeaway of this part of the talk is it's not obvious that thermalization happens as usual when charges don't commute. This conclusion should be a little surprising because we said thermalization is ubiquitous. It takes something special for a system not to thermalize as usual. For instance, it takes thermodynamic work or a special regime of quantum matter. When charges don't commute, two derivations of the thermal state's form break down. Also, the global charges, since they don't commute, don't share an eigenbasis. So they don't necessarily share an eigenspace, or eigenspaces in abundance. So a microcanonical subspace doesn't necessarily exist. Now, I'll review what a microcanonical subspace or state is and why it matters in thermodynamics. Let's go back to this simpler problem in which the system and environment exchange just heat and particles. Suppose we want to convince ourselves that the small system is in a thermal state. We'll suppose that the whole system is in a microcanonical state. So we'll suppose the whole system has some particular number of particles and has a pretty well-defined energy. So it's in a microcanonical subspace. Then we attribute to the global system a microcanonical state, which is the projector onto this subspace normalized by the dimensionality of the subspace. We trace out the environment to obtain the reduced state of the system of interest, which turns out to be the canonical state, the relevant thermal states, if the system and environment couple just weakly. We can extend this argument. Suppose that the system and environment exchange more charges that commute with each other. Now the microcanonical subspace is an eigenspace shared by all those charges. Apart from the Hamiltonian is special because it generates the time evolution. But if the charges don't commute with each other, then, as we said, they don't share an eigenbasis, they don't necessarily share an eigenspace, they almost certainly won't share many, and so we don't have recourse to the microcanonical subspace, which is essentially the very first step in this argument that we use to convince ourselves that the small system should be in the thermal state. So if a Hamiltonian conserves non-commuting charges, it has degeneracies. So some of the energies will equal each other. And degeneracies tend to, this result is because of Schur's lemma, a result in group theory. And degeneracies tend to throw wrenches in arguments for thermalization. Let's see. I'll probably have to skip this result, even though I like it a lot, particularly this paper that I did not co-author. Also, this result, which I like a lot, it's by a colleague at Duke, but I'll have to skip it as well. It has a more quantum computational flavor, so if any of you have that kind of an interest, feel free to ask about it during the question and answer session. And the result that I'm going to focus on for a few more minutes is that non-commuting charges conflict with the eigenstate thermalization hypothesis, which I'll review now. By the way, this paper down here, let's see, so this is a general abstract theory paper, and this is a numerical test of a replacement for the eigenstate thermalization hypothesis, which is a toolkit for helping us understand how quantum many-body systems thermalize internally. And I wanted to point out that this numerical paper has as a co-author Jade Leshek, who is a senior undergrad at the University of Maryland. She's a fantastic student, very, very driven, very well organized, and also applying to grad schools. So that's Jade. So the eigenstate thermalization hypothesis is, as I mentioned, toolkits that we use in many-body physics for understanding how a system thermalizes internally. One of the more obnoxious things about the eigenstate thermalization hypothesis is it has a ridiculous number of syllables, so I might use the acronym ETH. It's been used in a lot of subfields of quantum many-body physics, and it tells us about a system that has many degrees of freedom and is governed by a Hamiltonian that we might want to call chaotic or non-integrable. So what do I mean by internal thermalization? Well, consider some typical local operator O. We can represent it as a matrix relative to the energy eigenbasis. The eigenstate thermalization hypothesis is an ansatz for the structure of the elements of that matrix. Now suppose that we have an operator O and a Hamiltonian that obey the ETH, and suppose the Hamiltonian is non-degenerate, and suppose that we have our system started off in a microcanonical subspace. Then we can conclude that this system will thermalize locally in the following sense. Suppose that we measure the expectation value of this operator at some time t, and then we average over time. This time average will equal the appropriate thermal average to within small corrections. Here, n denotes the size of the global system, and I'm using O the way that my many-body physics friends do to mean scales as. And people in quantum information theory might be used to a slightly different meaning. We already concluded that if the Hamiltonian conserves non-commuting charges, it will have degeneracies, and we can't rely as usual on microcanonical subspaces. So what about the eigenstate thermalization hypothesis itself? Well, also the eigenstate thermalization hypothesis we can't rely on. And from now on in this part of the talk, I'm going to focus on charges that are the components of angular momentum, as in our concrete example. We said that the ETH is an ansatz for the forms of the elements of a matrix that represents a local operator relative to the energy eigenbasis. But the Wigner-Eckert theorem already dictates the form of those matrix elements. The Wigner-Eckert theorem, you'll probably recall, is something that we study on the way to qualifying exams in physics grad school. I don't have time here to explain all the formalism. Feel free to ask during the question and answer session. Here I'll just illustrate it with a simple example. Suppose that we have an atom that starts off with some amount of angular momentum, and the atom absorbs a photon. Then we ask afterwards, if we perform a measurement, what is the probability of finding this amount of angular momentum in the atom? Or more precisely, what is the probability amplitude? This probability amplitude, according to the Wigner-Eckert theorem, is a product of two particular factors. Now, if you look again at this probability amplitude, you might notice that it is actually the elements of a matrix that represents an operator relative to the energy eigenbasis that conserves the spin components. So the Wigner-Eckert theorem butts heads with the ETH, as in both of them are trying to dictate the form of this matrix element. But the Wigner-Eckert theorem is a theorem. We know it's true. Whereas the eigenstate thermalization hypothesis, the ETH, is just an H. It's just a hypothesis. So the ETH loses out against the Wigner-Eckert theorem in the presence of non-commuting charges. So these were our premises and our argument for thermalization. This was our form of thermalization. Now all the premises are out the window. So what do we do? Do we have to abandon this really useful toolkit that's been around for a number of decades? So I had the pleasure and privilege of working with Mark Schrednitsky's group on proposing a non-abelian ETH. So a non-abelian eigenstate thermalization hypothesis looks like this. I'll present the cartoon version. Again, feel free to ask during the question and answer session for more details. We said we have a quantum many-body system and a favorite local operator. We represent the local operator relative to an energy eigenbasis as a matrix. What form do the matrix elements have? According to our hypothesis, a matrix element is a coefficient times the sum of two terms. One is called the diagonal term because it's non-zero only on the block diagonal of the matrix. And the other term, very creatively, is called the off-diagonal term because it can be non-zero also off the block diagonal. The diagonal term tells us about the average behavior of the time average behavior. And the off-diagonal term tells us about fluctuations over time in the expectation value of O. This coefficient makes the hypothesis consistent with the Wigner-Eckert theorem, and now all of the parts of the hypothesis depend on spin-type quantum numbers. Okay. We would like to use this non-abelian ETH to learn about thermalization in the presence of non-commuting charges. So we should review our premises and our argument for thermalization. We had three premises. We've solved the problems with two of them. And now we need to deal with the microcanonical subspace problem. I won't have time to talk about the details. Again, feel free to ask about them later. The basic idea is we relax the notion of a microcanonical subspace to the notion of an approximate microcanonical subspace. The charges usually can't have sharply well-defined values simultaneously because of the non-commutation, so we let them have fairly well-defined values. I'll just skip the next slides. All right, so suppose that we take our non-abelian ETH. We suppose that our initial state is in an approximate microcanonical subspace. That preparation can be realized experimentally. It was realized in the trapped ion experiment. Now we want to learn about thermalization. So we want to compare the time average of our expectation value of our favorite operator O to the thermal expectation value. The thermal expectation value is the trace of the operator with the appropriate thermal state, the non-abelian thermal state. And we compute the time average by, again, supposing the state is originally in an approximate microcanonical subspace. Then we calculate the expectation value at some time t prime. We average over time and take the limit as t approaches infinity. That's our time average. So how do these two compare? We can ask about two regimes. Suppose that the magnetization is extensive. It grows like the system size, as large as possible. The time average minus the thermal average will be as small as usual. The corrections will be like 1 over the global system size. So we recover a qualitative result of the ordinary situation in which there are no non-commuting charges, but the recovery is rather more difficult. Usually the proof is a page, and here it's a few appendices. Then we can go to the opposite extreme and suppose that the magnetization vanishes. It's as small as possible. Now, there is a condition under which the time averaged expectation value minus the thermal expectation value is polynomially larger than the ordinary correction. We derive this result under an assumption that we believe is physically reasonable and, of course, need to check numerically and ideally experimentally. This result has a fundamental implication and a possible application, or a fundamental implication and a possible application. First, it indicates that under certain conditions, a system with non-commuting charges might not get down quite as far as usual to thermalization. So since thermalization goes hand in hand with the arrow of time, maybe these quantum systems don't quite experience the arrow of time as strongly as usual. And second, if a system doesn't get down to thermal equilibrium quite as much as usual, maybe it retains some extra information about its initial conditions, so maybe we can use it to store information in a quantum memory. Does anyone have questions at this point? Yes, so in case people didn't hear it, the question is about the basis of the Hamiltonian, the eigenbasis of the Hamiltonian that we're using in the statement of the non-abelian ETH. I definitely did not specify that basis because this is a colloquium rather than a seminar, so you definitely picked up on something that I did not say. So thank you for asking. We chose a basis. Again, here we were talking about spins. We expect you can generalize the result to different sets of non-commuting charges. Here we were focusing on charges that are the x, y, and z components of spin or angular momentum. And you can always rotate your axes so that the initial state has a magnetization just along the z direction. And so we chose the basis that all of us know. It's shared by the vector sigma x, or vector s squared and sz in addition to the Hamiltonian. So we chose that basis basically because there is rotational symmetry. And this turns out to be a very useful quantity to have in deriving these results about thermalization. Any other questions?
So your S there is the global charge, which is guaranteed to be true?
This vector S squared is the vector of the components of the total angular momentum.
Okay, and it commutes H or does not?
It does.
Okay.
That's why it shares an eigenbasis with H and resolves the degeneracy. Okay. I think there are lots of opportunities for future work. One is we now have something of a puzzle. We have a little pile of evidence indicating that in some ways the non-commutation of charges hinders some facets of thermalization, but we also have a little pile of evidence suggesting the opposite. We just saw 6 pieces of evidence indicating that in some ways the non-commutation of charges hinders features of thermalization, but there are arguments in the opposite direction. For example, one that some people here might be familiar with is that there is a regime of quantum matter called many-body localization in which thermalization happens very slowly. You can take a many-body localized system and force non-commuting charges on it, and you will destabilize the many-body localization. So even an infinitesimally small perturbation that breaks the symmetry will make the system thermalize at the ordinary rate. I don't have time to go through all of these examples, but that is one example. Now, these results from these 2 different piles technically don't conflict with each other because each result was derived with its own particular setup, but conceptually they conflict with each other. So I think we need to reconcile them. And maybe one pile will win out. In case you couldn't tell, I was rooting for the first pile of hindering thermalization, but we need a more complete story. And I also think that we should go around to every phenomenon in chaos and thermodynamics and ask, does anything change? And if so, what changes if the dynamics conserve quantities that don't commute? There are lots of facets of thermodynamics to check, in part because the tools of quantum information science have recently been applied to discover new stages of thermalization of quantum many-body systems. And this notion of non-commuting charges originally developed within the intersection of quantum information and quantum thermodynamics, but now is a great time for it to spread to atomic, molecular, and optical physics, condensed matter, and so on, and also kind of assimilate with those fields and toolkits. So in summary, we looked at non-commuting charges in quantum thermodynamics. We can take a textbook undergraduate setting, make one tweak related to non-commutation, and find that our expectations about thermalization break down. We looked at the concrete example of a chain of qubits in which the x, y, and z components of spin were conserved. We asked what changes in thermodynamics when charges don't commute, looking at the example of the eigenstate thermalization hypothesis, which could, under certain circumstances, lead to a kind of anomalous thermalization. And we saw that there is a lot to be done. This is the perspective that I mentioned earlier. So if you're interested in looking into the subfield as a whole, then I would point to that as a resource. My group has been kind of obsessed with this subfield for a few years, so this is all our work in case you're interested. And if you're interested in more of a story about how the subfield arose, then I can point to chapter 12 of that book. So, thanks for your time. The question is about the arrow of time, it can be, or it's related to a Crookes fluctuation theorem, which involves the probability of a forward process and the probability of a reverse process. Is there an analog of that here? In this paper, we wanted to derive fluctuation theorems for non-commuting charges, and so we derived integral fluctuation theorems. So the setup was, suppose that you have the analog of a metal rod with a hot end and a cold end. Energy flows. As it flows, it produces entropy. And one can write down a fluctuation theorem that tells us about properties of the probability distribution over the possible amounts of entropy that could be produced in the next trial. So we said, suppose that you have two systems, maybe two different qubits, that have, instead of different temperatures, different effective temperatures associated with sigma x and sigma y and sigma z. And suppose that you couple them so that these charges can flow between them. It turns out that the notion of entropy production doesn't entirely make sense anymore. There are three very widely used formulae for entropy production that all equal each other ordinarily, but it's not even clear how you can even measure entropy production when there are non-commuting charges, because any time you want to measure how much stuff has flowed into this system to measure entropy production, but when you measure how much stuff has flowed into this system, you disturb the system, and you disturb the amount of another charge that has flowed into that system. So the problem is even worse than usual in ordinary quantum thermodynamics, where you just worry about eliminating coherences of the state relative to the energy eigenbasis when you make a measurement. So we had to generalize the notion of entropy production. So there are three different formulae for entropy production that all converge if everything commutes with each other. And we derived a fluctuation, an exchange fluctuation theorem for each of those. Two of them have corrections that depend explicitly on the non-commutation. One of them is correction-free.
So thank you for this very nice colloquium. You showed us, talked about an example where thermalization is slower than expected. What could cause thermalization to be faster?
The question was about the speed of thermalization. Near the end of the talk, I mentioned there's a regime of quantum matter, many-body localization, in which thermalization happens more slowly than usual. What could speed up the rate of thermalization? I guess increasing the temperature difference. I guess I haven't really thought about that. That is an interesting question. I'm so biased to think about the opposite direction because I guess, there's a whole industry related to holding off on the effects of aging. We like to have memories that retain information for long times in everyday life and in computers and so on. So that's what I've thought about more, but maybe I shouldn't have thought about it more. Okay.
I was wondering if you had any opinions or insights or relations to the difference between Markov evolution in a both quantum and non-Markovian evolution.
Okay, the question is about the difference between Markovian and non-Markovian evolutions in open quantum systems. Were you looking for something in particular? They definitely can have different, or they definitely have different characters, can have implications for storing memory, acting back on the system. I have a grad student who's currently obsessed with non-Markovianity, so maybe I should have brought him here so he could answer any question about non-Markovianity. Did you have any?
I was just wondering, if you run across any connections, it sounds like you're going to.
Any connections to non-commuting charges?
Oh, yeah,
Or
yeah.
I haven't run into connections to non-commuting charges, but that would certainly be nice. So
Or
usually,
at least, quantum thermodynamics in general.
they're
With Markovian evolution, you definitely go through some steady state.
yes. So maybe is the question about has non-Markovian evolution been studied in quantum thermodynamics, and what are maybe some quantum signatures within it?
Yeah.
Okay. It's Yeah, it's been kind of a popular topic within quantum thermodynamics during the past few years. And there are even multiple definitions of quantum non-Markovianity. So one feature within quantum non-Markovianity is a lack of CP divisibility. So very commonly, we'll suppose that there is a process, maybe a Markovian process, so a memoryless process, such that we can pick any points at any place in the middle and separate our process into two smaller processes of similar character. Just when we, how do we do that quantum mechanically? If we were to say, observe the system at this point, then we would change the state. And so that creates kind of an extra dimension. But yes, I don't work on non-Markovianity myself, but there's a lot of good literature from the past few years and also beforehand. The question is about how do thermal phase transitions fit into this scheme? The one study that I know of that has combined phase transitions with non-commuting charges is the many-body localization setting that I mentioned earlier. Well, okay, we can't say now that many-body localization is a phase necessarily. So that's why I said that many-body localization is a regime of matter. In some ways, it acts like a phase. So there is some kind of transition between the many-body localization regime and a more thermal regime. And some folks showed that if you have a many-body localized system and you make it conserve non-commuting charges, then the many-body localization becomes unstable to any small symmetry breaking perturbation. The system will flip over into the strongly thermalizing regime. So it sounds like you're drawing an analogy with a first-order phase transition, as in when a first-order phase transition happens, as the system kind of swallows up more energy, its temperature is not changing because that energy is being used in order to change its structure. And so we don't want to associate a thermal state with the system. And we said similarly here, it wasn't clear at first that it made sense to write down the thermal states form. And even still, we're not sure that the system gets down to thermal equilibrium quite as much as usual. I could see that there's a parallel there. Are you asking whether the ETH holds in the presence of non-commuting charges and a first-order phase transition? I'm not familiar with applications of the ETH in the presence of, or specifically to a Hamiltonian at a first-order phase transition.
Okay, last question.
I was wondering whether you explored or how you look about non-argument for thermodynamic treatment for non-commuting.
The question is about Landauer's principle. So Landauer's principle is the notion that there is a fundamental thermodynamic cost for erasing a bit of information or a qubit. Landauer's bound states that on average to erase a bit of information costs Boltzmann's constant times the temperature of the ambient environment times log 2. And were you asking, is there a Landauer's bound type result for the presence of non-commuting charges?
Yeah, or like thermodynamic treatment.
In the context of non-commuting charges or just generally? Okay, in the context of non-commuting charges. No, Not that I know of. Or, well, no. Actually, let's see. So there have been papers about how you can, if you are erasing a bit or maybe a qubit, you can spend some resource other than work. We usually think of ourselves as spending work that gets dissipated as heat in order to erase a bit of information, but work that comes from, or that work is just one type of resource that we could spend. Instead, we could spend the effective free energy in a chemical potential gradient, or one topic that was studied by John Vaccaro and co-authors was how we can spend angular momentum in order to erase a bit. They were focusing on just one component of the angular momentum, but we should be able to generalize it to multiple components. But I'm not sure that anyone's written it out.
All right. Let's thank Nicole again for a fascinating